Welcome to our exploration of the thermal properties of matter. In this chapter, we'll uncover how heat and temperature influence everything around us, from the expansion of solids to the mysteries of black body radiation. Understanding these concepts is crucial not only for science students but also for anyone curious about the world's inner workings. As we journey through each topic, you'll see how thermal properties shape daily life and major engineering feats. Let's begin by laying the foundation. What exactly are heat and temperature, and why do they matter so much? Heat and temperature are often used interchangeably, but they're quite different. Heat is a form of energy that flows from a hotter object to a cooler one, while temperature measures how hot or cold something is, reflecting the average kinetic energy of its particles. For example, when you touch a warm mug, heat flows from the mug to your hand. Temperature, on the other hand, tells you how much energy the particles in the mug have. This distinction is fundamental to understanding all thermal phenomena. Thermal expansion is the tendency of matter to change its shape, area, and volume in response to a change in temperature. When substances are heated, their particles move more vigorously, causing them to take up more space. This effect is seen in solids, liquids, and gases, though the degree of expansion varies. Thermal expansion is why bridges have expansion joints and why mercury rises in a thermometer. It's a key concept in both everyday life and engineering. Solids expand when heated because their atoms vibrate more and push each other apart. However, since the particles in solids are tightly packed, the expansion is usually small but significant in engineering. For example, railway tracks are laid with small gaps to allow for this expansion. If not, the tracks could buckle on hot days. Understanding how solids expand helps engineers design safer structures and machinery. Liquids expand more than solids when heated because their particles are less tightly bound. This property is used in thermometers, where mercury or alcohol rises as the temperature increases. The expansion of liquids is also important in everyday appliances like car radiators, which must be designed to accommodate changes in volume as the engine heats up. Understanding this helps prevent leaks and damage. Gases expand the most when heated because their particles are far apart and move rapidly. This is why a balloon inflates when warmed and why hot air rises. The expansion of gases is crucial in engines, weather patterns, and even in our lungs as we breathe. Engineers and scientists must account for this property in designing everything from air conditioners to rockets. Coefficient of linear expansion is a measure of how much a material's length changes per degree of temperature change. It's a property unique to each material. For example, metals generally have higher coefficients than glass or stone. This value helps engineers predict how much a bridge or a metal rod will expand or contract with temperature changes, ensuring structures remain safe and functional. Coefficient of volume expansion describes how much a material's volume changes with temperature. It's especially important for liquids and gases where volume changes are more noticeable. For example, when water is heated, it expands and can overflow a container. This concept is vital in designing containers, engines, and even weather prediction models. Specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Different materials require different amounts of heat to change temperature. For example, water has a high specific heat, which is why it takes a long time to boil. This property is crucial in climate science, cooking, and engineering applications like heating systems. Calorimetry is the science of measuring the amount of heat transferred to or from a substance. It's used in laboratories to determine specific heat capacities and study chemical reactions. Calorimeters are devices designed for this purpose, allowing scientists to measure energy changes accurately. This technique is essential in food science, chemistry, and engineering. The principle of a calorimeter is based on the conservation of energy. The heat lost by a hot object equals the heat gained by a cold one, assuming no heat is lost to the surroundings. This allows accurate measurement of heat transfer in experiments. Calorimeters are insulated to minimize heat exchange with the environment, ensuring precise results in scientific studies. Latent heat is the heat required to change the state of a substance without changing its temperature. For example, when ice melts to water or water boils to steam, energy is absorbed but the temperature remains constant. This hidden energy is crucial in understanding phase changes and is widely used in refrigeration and meteorology. Latent heat of fusion is the energy needed to change a solid into a liquid, like melting ice. Latent heat of vaporization is the energy required to change a liquid into a gas, such as boiling water. Both processes involve energy absorption without a temperature change, but vaporization typically requires more energy than fusion. These concepts are vital in weather systems and industrial processes. Thermal conductivity is a material's ability to conduct heat. Metals like copper and aluminum have high thermal conductivity, making them ideal for cookware and heat exchangers. Insulators like wood or plastic have low thermal conductivity, which is why they're used for handles and building insulation. This property is essential in designing efficient heating and cooling systems. Induction is the transfer of heat through a material without the movement of the material itself. It occurs mainly in solids where particles pass energy to their neighbors. For example, a metal spoon in hot soup becomes warm because heat travels from the soup to the spoon's handle. Understanding conduction helps in designing cookware, building insulation, and electronic devices. Convection is the transfer of heat by the movement of fluids such as liquids or gases. Warm fluid rises while cooler fluid sinks, creating a circulation pattern. This process is seen in boiling water, atmospheric currents, and ocean circulation. Convection is essential in weather systems, heating systems, and even in cooking. Radiation is the transfer of heat through electromagnetic waves without needing a medium. The sun warms the earth through radiation, and you feel warmth from a fire even if you're not touching it. All objects emit some thermal radiation, but the amount depends on their temperature and surface properties. Radiation is key in energy transfer across space. Newton's law of cooling states that the rate at which an object cools is proportional to the temperature difference between the object and its surroundings. This law explains why hot coffee cools faster in a cold room than in a warm one. It's widely used in engineering, food science, and even forensic investigations to estimate time of death. Blackbody is an idealized object that absorbs all radiation falling on it and emits radiation at a maximum rate for its temperature. Blackbody radiation is crucial in understanding how stars emit energy and forms the basis for technologies like infrared cameras. This concept also led to the development of quantum physics. Greenhouse effect is the process by which certain gases in Earth's atmosphere trap heat, keeping the planet warm enough to sustain life. Without it, Earth would be too cold. However, excessive greenhouse gases from human activities are causing global warming. Understanding this effect is vital for addressing climate change and protecting our environment. Studying thermal properties is essential in engineering because materials behave differently at various temperatures. Engineers must consider expansion, conductivity, and heat capacity when designing bridges, engines, and electronic devices. Ignoring these properties can lead to failures, inefficiency, or even disasters. That's why thermal science is a cornerstone of modern engineering. Thermal properties aren't just for scientists and engineers, they affect our daily lives. From cooking food to keeping homes warm, understanding how heat moves and how materials respond to temperature helps us make better choices. Even simple actions like using a thermos or wearing layers in winter rely on these principles. In construction, thermal expansion must be considered to prevent structural damage. Bridges, pipelines, and buildings are designed with joints or flexible materials to accommodate expansion and contraction. Without these features, structures could crack or buckle as temperatures change throughout the year. Appliances like refrigerators, ovens, and air conditioners rely on materials with specific thermal conductivities. Metals are used where rapid heat transfer is needed, while insulators keep heat in or out as required. Choosing the right materials ensures efficiency and safety in household devices. Large bodies of water like oceans and lakes have high specific heat capacities. This means they absorb and release heat slowly, moderating the climate of nearby regions. Coastal areas often have milder temperatures than inland areas thanks to the thermal properties of water. Cooking is a practical example of heat transfer. Whether boiling, frying, or baking, heat moves from the stove or oven into the food by conduction, convection, or radiation. Understanding these processes helps cooks achieve the perfect meal and avoid burning or undercooking. Thermal insulation keeps homes comfortable by reducing unwanted heat loss or gain. Materials like fiberglass, foam, and even thick curtains help maintain indoor temperatures. Good insulation saves energy and money, making it a smart investment for any household. Vehicles and transportation systems must account for thermal expansion. Train tracks, airplane wings, and car engines all experience temperature changes that can affect performance and safety. Engineers use special materials and designs to ensure reliability in all weather conditions. Electronic devices generate heat during operation. Managing this heat is critical to prevent overheating and ensure longevity. Materials with high thermal conductivity like copper are used for heat sinks, while insulators protect sensitive components. Effective thermal management is key to modern electronics. Nature also demonstrates thermal conductivity. For example, animals like polar bears have fur that acts as an insulator, keeping them warm in cold climates. Rocks and soil conduct heat differently, affecting plant growth and weather patterns. Observing nature helps scientists develop better materials and technologies. Everyday objects like glass jars and metal lids expand and contract with temperature changes. That's why a tight lid may loosen after running it under hot water. Understanding thermal expansion helps us solve simple problems and avoid accidents at home. Sports equipment like tennis rackets and golf clubs are designed with thermal properties in mind. Materials must withstand temperature changes without warping or losing strength. Even playing surfaces like ice rinks or artificial turf rely on controlled heat transfer for optimal performance. Artists and designers must consider thermal expansion when working with materials like metal, glass, or ceramics. Temperature changes can cause cracking or warping, affecting the final piece. By understanding thermal properties, creators can produce more durable and beautiful works. Medical devices like thermometers and incubators rely on precise thermal properties for accurate readings and safe operation. Even treatments like cryotherapy or heat therapy use controlled temperature changes to heal or relieve pain. Understanding heat transfer is vital in healthcare. Food preservation methods such as freezing, canning, and pasteurization depend on controlling heat transfer. Freezing slows down bacterial growth while pasteurization uses heat to kill harmful microbes. Understanding thermal properties helps keep our food safe and fresh. Spacecraft and satellites face extreme temperature changes in space. Engineers use materials with specific thermal properties to protect equipment and astronauts. Insulation, heat shields, and radiators are all designed to manage heat in the harsh environment of space. Clothing materials are chosen for their thermal properties. Wool and synthetic fibers trap air, providing insulation in cold weather, while cotton allows heat to escape, keeping us cool. Understanding these properties helps us dress appropriately for any climate. Renewable energy systems like solar panels and geothermal plants rely on thermal properties to convert heat into usable energy. Efficient heat transfer and insulation are key to maximizing output and reducing losses. This knowledge supports the transition to sustainable energy sources. Farmers use thermal properties to protect crops from frost, manage greenhouse temperatures, and dry grains. Understanding how heat moves through soil and air helps improve yields and reduce losses. Technology like soil sensors and climate-controlled greenhouses relies on these principles. Water supply systems must consider thermal expansion and contraction of pipes to prevent leaks and bursts. Hot water systems in particular use expansion tanks and flexible joints to accommodate changes in volume. Proper design ensures reliable and safe water delivery. Museums and galleries control temperature and humidity to preserve artworks. Fluctuations can cause paintings to crack or sculptures to deteriorate. Understanding thermal properties helps conservators protect cultural treasures for future generations. Disaster response teams use knowledge of thermal properties to fight fires, manage heat waves, and provide shelter. Materials with high insulation are used in emergency blankets, while cooling centers help people stay safe during extreme heat events. Tires, brakes, and engines all generate heat during use. Managing this heat is essential for vehicle safety and performance. Engineers design cooling systems and use heat-resistant materials to prevent failures and accidents on the road. Modern buildings use advanced materials and designs to manage heat flow. Double-glazed windows, insulated walls, and reflective roofs help maintain comfortable indoor temperatures and reduce energy costs. Architects and engineers rely on thermal science for sustainable building solutions. Summary: the thermal properties of matter influence nearly every aspect of our lives, from the food we eat to the buildings we live in. By understanding heat, temperature, and how materials respond to them, we can design safer, more efficient, and more sustainable solutions for the future. The study of thermal properties is not just academic, it's a key to unlocking the secrets of the world around us.